Good morning, this is Dr. Kumar Arya, Associate Professor in Department of Chemical Engineering, IIT Jalandhar. Today I am going to explain the diffusion of gas with heterogeneous reactions. So this is actually a typical case where you have a catalyst and heterogeneous reaction is taking place on the catalyst surface. So here you have something like that. If we'll take it expanded form of this, is look like this. So here you have this catalyst, and whatever amount of A reaches at this particular point totally is being consumed. So this is case of instantaneous reaction here, and the product is being formed which diffuses back to the stagnant gas film. So this is Z coordinate and total film thickness is delta. So reaction is being considered, this reaction, dimerization reactions. 2A is getting converted to B, so B equal to A2. So for instantaneous reactions, dCA upon dt equal to del dot Na plus Ra, dCB upon dt equal to del dot Nb plus Rb. For heterogeneous no bulk reactions, and this one Ra equal to Ra0, Rb equal to 0, steady state del Ca upon del T equal to 0, del Cb upon del T 0. So this term is 0, this one is 0, this and this is 0. Excessively fast reactions, so these terms are 0. So finally you have this. So this is del Na upon del Z, so del Nb upon del Z. So del Na upon del Z upon this equal to 0. So NaZ is constant. dNbZ upon dZ equal to 0. So NbZ is constant. NaZ equal to minus 2. NbZ at Z equal to delta from reaction stoichiometry. Now the fixed law says that NaZ equal to minus C dAb dXA upon dZ plus XA NaZ plus NbZ. So we can substitute the value of NbZ from here. So we will get here that NaZ equal to 1 minus XA by 2 minus C dAb dXA upon dZ. So we can put dXA terms to one side and dZ terms to one side. We can integrate that. We will get minus 2 ln 1 minus XA by 2 equal to minus NaZ into Z upon C dAb plus C1. So this is equation number 1. We have boundary condition that x equal at Z equal to 0, XA equal to XA0 in the beginning of the film. At x equal to delta, the catalyst, the interface, XA equal to 0. This totally being consumed. Instantaneous fast reactions. So if we substitute first into this, we will write here this term is 0. So we will get C1 equal to minus 2 ln 1 minus XA0. Now we will substitute this condition there and value of constant C1 here. So we will get this another equation that NaZ equal to minus 2 ln 1 minus XA0 by 2 C delta AB upon delta dAb upon delta. Now from equation 1 we can write minus 2 ln 1 minus XA by 2 minus dNaZ C dAb Z minus 2 ln 1 minus XA naught upon 2. So this we can take this term to here. We can write here the expression for NaZ Z upon C dAb. So we can simplify these two expressions here. So we will get here 2 ln 1 minus XA by 2 upon 1 minus XA naught by 2 equal to NaZ Z upon C dAb. This we already have, that NaZ equal to minus 2 ln 1 minus XA naught by 2 C dAb by delta. We can substitute this expression here, and then we will end up of this equations here. So we substitute this here, arrange it here. So we will get ln 1 minus xa by 2, 1 minus xa naught by 2 minus z upon delta ln 1 minus xa naught by 2, and nz is given by minus 2c dab upon x upon delta ln 1 minus xa naught by 2. So this is the rate of consumption of a per unit area per unit time. This equation can help to find the mole fractions or concentrations at any position z within the film. Now for in case of finite rate of the reaction, in case of instantaneous reaction, this xa comes to be 0 at the catalyst surface, but in case of finite reactions this will not be the case, so we have to find this again, so that at the surface we can get our rate of the reaction is minus kCa minus kc into xa. So this would be the condition of at this particular place here. Now NaZ equal to this here, so NaZ equal to RSA. Whatever flux is coming, same rate is being consumed by the reactions here. So boundary conditions now that Z equal to 0, Xa equal to Xa0, Z equal to delta, NaZ equal to minus RSA equal to KCXA. So Xa delta is NaZ upon Ck actually. Now from boundary condition 1 we will get C1 equal to minus 2 ln 1 minus Xa naught by 2. From second boundary condition, this one we can substitute here that Xa delta, then NaZ C dab delta minus 2 ln 1 minus Xa by 2. So for that we can get the expression of NaZ from here. Now we can substitute the expression for NaZ now in terms of Ck upon dab Xa delta. So this you can arrange it here. We can get Xa delta expression here is 2 dab delta k ln 1 minus Xa delta by 2 minus Xa naught by 2. Then we can write expression for NaZ. So NaZ is actually is given by this 2c dab upon delta, multiply this, so you can see the change from here to here. The k is not here, the k into Xa delta and divided by c would be equal to your NaZ. Now NaZ equal to this against 2c dab upon delta ln 1 minus NaZ. So this is Xa delta expression here, so NaZ upon 2ck. So this you can substitute here, so you will end up with minus 2 ln 1 minus Xa by 2 equal to minus 2 NaZ upon c dab z minus 2 ln Xa naught by 2. So this you can arrange it and you will finally end up with ln 1 minus Xa by 2 1 minus Xa naught by 2 z upon delta ln 1 minus Xa delta by 2 1 minus Xa naught by 2. So this is the expression just to find concentrations at any Z for in case of finite rate of reactions. So this is of diffusion of gas through the heterogeneous reactions. Thank you.